Hello, fellow Physics 106 students. I hope you're having a great day, because I certainly am. Of all the various topics available, I was lucky enough to snag a slot to talk to you about Van de Graaff generators. I hope you find this video enlightening and entertaining, as I put a lot of work into it. I think it turned out well. If you enjoyed this video, please let me know by hitting the like button, and don't forget to subscribe. Without further ado, the Van de Graaff generator. In this video, I'm going to answer a few questions for you. What is a Van de Graaff generator? Where did these things come from? Who invented the Van de Graaff generator? Why do they work? What are the principles involved? What are they useful for? Let's see some real-life applications. And perhaps most importantly, where do I get one? By the end of this presentation, you may be so excited about Van de Graaff generators that you just have to have one of your very own. I've done a little digging for you, and you have a few options. Stay tuned to the end to find out more. First, what is a Van de Graaff generator? According to an undisclosed but extremely reliable source, a Van de Graaff generator is an electrostatic generator which uses a moving belt to accumulate electric charge on a hollow metal globe on the top of an insulated column, creating very high electric potentials. Basically, it's a machine that uses principles of static electricity to separate electric charges in such a way that they can be useful to us. More than likely, if you're watching this video, you've already seen these generators in classroom demonstrations. And if your professor wasn't careful, he probably shocked himself with it at least 3 times per class period during the unit on electricity. Thankfully, he only had a small one. The big ones are kind of scary. Where did these apparently dangerous but strangely captivating contraptions come from? As you've probably guessed, they were invented by a scientist named Van de Graaff. To quote the Encyclopedia Britannica, Robert Jemison Van de Graaff, born December 20th, 1901, in Tuscaloosa, Alabama, was an American physicist and the inventor of the aptly named Van de Graaff generator. Throughout the course of his education, he was inspired by the other great scientists such as Marie Curie and J.S.E. Townsend, with whom he interacted, to investigate atomic physics and electricity. While at Oxford, Van de Graaff was impressed with the need for a source of energetic beams of subatomic particles for the study of atomic behavior. He conceived the idea for the Van de Graaff generator and, upon returning to the United States in 1929, continued to develop it. Van de Graaff built his first generator in the early 1930s. So how do Van de Graaff generators work? Let's walk through it. To quote extensively our beloved and certainly reliable yet undisclosed source, a simple Van de Graaff generator consists of an insulating belt, indicated here. In this case, is made of rubber, moving over 2 rollers of differing material, one of which is surrounded by a hollow metal sphere. 2 electrodes, in the form of comb-shaped rows of sharp metal points, are positioned near the bottom of the lower roller and inside the sphere, over the upper roller. Comb 2 at the top is connected to the sphere, and comb 7 to ground. The method of charging is based on the triboelectric effect. The mechanism of this effect is explained in another video, but put briefly, it describes the way that simple contact of dissimilar materials causes the transfer of some electrons from one material to the other. For example, the rubber of the belt will become negatively charged, while the acrylic glass of the upper roller will become positively charged. For another example, consider Veery the cat, who was excited about the new box to play in, and didn't wait for the packing peanuts to get dumped out first, but I digress. The belt carries away negative charge on its belt carries away negative charge on its inner surface, while the upper roller accumulates positive charge. Now here's where things get tricky. Next, the strong electric field surrounding the positive upper roller induces a very high electric field near the points of the nearby comb. At the points, the field becomes strong enough to ionize air molecules, and the electrons of those molecules are attracted to the outside of the belt, while positive ions go to the comb. At the comb, they are neutralized by electrons that were on the comb, thus leaving the comb and the attached outer shell with fewer net electrons. The excess positive charge is accumulated on the outer surface of the outer shell, leaving no field inside the shell. Electrostatic induction by this method continues, building up very large amounts of charge on the shell. How much charge are we talking? The potential difference achieved by modern Van de Graaff generators can be as much as 5 megavolts. A tabletop version can produce on the order of 100,000 volts and can store enough energy to produce a visible spark. Just thinking about such high voltages might make your hair stand on end. But as it turns out, the number of volts isn't the scary part about electricity. When someone gets hit by lightning, the thing that fries them is the current, measured in amps. Viry tells us about the relationship between volts and amps. The 100,000 volts produced by the tabletop generator, if discharged over a high resistance, like say through dry air, will result in a current too low to cause lasting damage to a human. But all things considered, it's still better to treat these things with respect and caution. What are Van de Graaff generators used for today? As I mentioned before, they were invented as particle accelerators for the purpose of studying subatomic particles. Since its invention in the 1930s, the Van de Graaff generator has been improved over time and has inspired other kinds of particle accelerators like this one, the Large Hadron Collider in Switzerland. The Collider's website describes it in these words: "The Large Hadron Collider is the world's largest and most powerful particle accelerator. It consists of a 27-kilometer ring of superconducting magnets with a number of accelerating structures to boost the energy of the particles along the way." Perhaps you feel, as I do, that the Van de Graaff generator is one of the more entertaining pieces of equipment among the researchers' resources. Well, the Boston Museum of Science certainly agrees with me. They have in their care the largest air-insulated Van de Graaff generator in the world, and they use it several times a day for educational and entertainment purposes. Their shows teach museum patrons about the wonders of electricity and include a unique musical finale, where the Van de Graaff generator and its sidekick Tesla coils actually play music by ionizing the air. And finally, the moment you've all been waiting for: where can you get your hands on one of these? The simplest way, of course, is to go the same route you always take to get your fresh Nikes and order one on Amazon.com. As it turns out, you can get a fully assembled Van de Graaff generator for the low price of just $139.95. Your other options include building one yourself using household materials, or by signing my internet petition to require the Utah State government to deliver a functional desktop Van de Graaff generator to each Physics 106 student who sends them a signed request via mail. I guess thievery is also an option, but something about stealing a Van de Graaff generator rubs me wrong. Well, that's my presentation on the wondrous Van de Graaff generator and its complexities. Thank you so much for watching this video. I hope you enjoyed it as much as I did. Videos like this would not be possible without the existence and positive peer review comments of subscribers like you. Happy studying.